All right, today we're going to finish up chapter 5 in your textbook on gases. I'm pretty sure we can get it done today. So I'll just a quick tally of where we are. Today we're going to finish gases, then Wednesday we'll do review, and then 8th of March will be exam. 10th of March, 8th of March, no, 8th of March will be the next topic, which is thermochemistry. And that'll also be the day for exam. And then March 10th will be, is that a review or a buffer? Let me see. That's a buffer day. Okay. So we won't have a review on the next chapter, chapter 6, until the 22nd of March, after spring break. All right. I'll do that as much for me as for you guys. All right. So let's finish up chapter 5, and I'll share PowerPoints here. There we go. And let's turn that into a slideshow. And that's right. It'll show up when I click on it. I just want to move some stuff out of my way. There we go. That here. Okay. So we had finished. We had finished talking about the individual gas laws, Boyle's law, Charles' law, Avogadro's law, and then we combined them into a combined gas law. And now we want to talk about ideal gases and formulate an ideal gas law. Remember, when you're solving a problem using one of the gas laws or even the combined gas law, you need to know beginning conditions and ending conditions. And either one of the beginning conditions or one of the ending conditions is an unknown, and you can solve for it. But sometimes your situation is actually a state. You're right here, right now. These are the conditions with one unknown. You don't know how it got there or where it's headed. You're just right there at the state of that particular problem. You need a way to solve the problem under those conditions. And that's what we're going to do now. But we need some information about the ideal gas. What is the ideal gas? Fortunately, gases exist as very distant separated particles compared to liquids and solids. So they have very little interaction. But under certain circumstances, they do interact significantly. Under conditions of very low temperature, you can make a gas turn into a liquid. And in order to do that, of course, the molecules have to interact to hold together. Some gases you can even turn into a solid, like carbon dioxide. You can make dry ice out of it. So we need to know under what conditions do gases behave ideally. Well, first we need to know what we mean by an ideal gas, of course. And this is kind of well, that's really a trivial statement. Ideal gas is a perfect gas. So that really doesn't give us any information. What is a perfect gas? Okay. What we mean by that is an ideal gas, this perfect gas, stays a gas always, under all conditions of pressure and temperature. So if you cool it down, down to absolute zero, it'll stay a gas all the way down. Now, we know that's not true. All gases, when they get close to absolute zero, most of them turn solid, but there are a few that will stay liquid all the way down. But none of them stay gases all the way down to absolute zero. Under high pressure, what does that do? High pressure forces them closer together. So the chances of interaction is much greater. So an ideal gas would behave, a real gas would behave more ideally if the pressure is low. So the particles can be widely separated and have very little interaction. And under high temperature. So high temperature, low pressure tends to favor the ideal behavior of a real gas. We also consider ideal gases as point volumes. Remember in math class, I hope you remember, when they start introducing the topics of dimensions, this represents that little dot. That represents a point which has no dimensions. It doesn't have height, it doesn't have width, it doesn't have depth. It's just a point, right? If you go from this point to that point, you get a line. And the line, make it thicker. The line only has one dimension, in this case, width. If you put lines together, say in a shape like that, a rectangle or a square, that has two dimensions, right? Height and width. And of course, if we go back into the board, height, width, depth. Now that's the real gas molecule. It has height, width, and depth. It has a volume. But the ideal gas does not have a volume. And the reason we insist upon point molecular volume, right, a single point, no dimensions, is that way we don't have to deal with the real volume of a gas when they start getting close together. When they get close together, then the volume of the gas is a significant percentage of the total volume that is holding the gas together. Remember, gases, they don't have their own shape, they don't have their own volume, so you have to have a vessel to hold them. Well, if we treat gases as if there's no volume to the molecules, then we only have to deal with the confined volume. I already said this one. Ideal gases do not interact with one another. They are there in that confined volume, and they do strike one another from time to time. But when they do that, they behave as if they're just billiard balls. They just bounce off. No interaction, no attraction, no repulsion. They just slam, bounce off in whatever direction. And of course, last but not least, ideal gases obey all of the gas laws. They do not deviate at all from those relationships that we've defined. Okay. So we'll be sure I'm still on screen. There we go. All right, so what are real gases like? Well, we mentioned one, real gases do liquefy. They do solidify sometimes under very cold temperatures and high pressures. Right, so that's the real gas. They do actually have volume. Right, so when you compress the gas really close together, I mean under high pressure, molecules are close together, then that volume is a significant percentage of the total. It has to be taken into account when calculations are made. They do interact with other gases. A gas molecule can be polar, it can be nonpolar. If it's polar, then there's significant interaction, particularly water vapor, for instance. And they do interact with each other and the walls of their container. How do we know that they interact with the walls of their container? Because we can measure pressure. If gases did not interact with the walls of the container and anything that we stuck in there, right? Right? Like a pressure gauge. If they didn't interact with the walls of their container, we wouldn't be able to measure the pressure. So, all that being said, gases behave ideally, for all intents and purposes, under conditions of low pressure and high temperature. Now, what does that mean? Well, as it turns out, and fortunately for the early 17th century study of gases, room temperature is high temperature, right? Based on absolute zero, it's 273 degrees Celsius, which is pretty high. That's high temperature. Low pressure is 1 atmosphere pressure, as opposed to what? High pressure would be like 20 atmospheres or 100 atmospheres. That's high pressure. Low pressure is 1 atmosphere or less, or it could be up to 5 or 10 atmospheres and then still be considered low pressure as far as the behavior of the gases go. Okay, so now we're going to have to decide, how do you deal with a state problem? This is your situation now, not before and after, right now. So we're going to combine these laws into a form that allows us to make the calculations for a state situation. Just a little history lesson. This is called the ideal gas law. And it was first proposed by Emil Clapeyron in early 19th century. And I may have said before, but the 20th century was atomic chemistry. Atomic chemistry. 19th century was organic chemistry. Right, that's when advances were really made in understanding of organic reactions. The 18th century was gas chemistry. And then leading up to that, the end of the 17th century was actually general chemistry emerging from black magic, so to speak. So by the time the early 19th century came around, chemists were starting to work on organic chemistry, but they hadn't abandoned gas chemistry altogether. And they were refining their understanding of gases. Now, during the 18th century, most of the gases, the elements that exist as gases, were isolated and characterized, like oxygen, hydrogen, chlorine. And then the theories surrounding gases were more completely worked out. Emil Clapeyron was one of them, 1834. And this is what the gas, the ideal gas equation looks like. PV equals nRT. We know P is pressure, V is volume, N is the abbreviation for number of moles, T is temperature in Kelvin, and R is a special constant. It's known as the ideal gas constant. Now, how was it derived? Well, I thought they were going to, maybe I need to show. Where did it come from? All right, we know that pressure times volume divided by N times T is equal to a constant. Right? We showed that last week. Well, if you choose your units correctly, units and magnitudes of the measurements correctly for these, you can generate a constant that is useful under any conditions. And that's when we call it R. Now, if we choose atmospheres for pressure, 1 atmosphere, I'll come back to volume in a minute. Moles, 1 mole, 1 atmosphere, 1 mole of gas at 0 degrees Celsius. Actually, that's not right. Zero degrees Celsius is 273.16 K. Sorry, my mistake. And then the volume, 1 atmosphere pressure, 1 mole of gas at that temperature, what volume does it occupy? Experimentally determined. It occupies 22.4 liters. Now, if you resolve that into the numbers and the units for that value, you come out with 0.08206 liter atmospheres per mole K. Liter atmospheres per mole K. Right. So that's one of the ideal gas constants. There are others. It depends on what they're being used for, right? So this one, instead of liter atmospheres, it has joules in it. So if you're doing a calculation that requires the gas constant and you're looking for energy, then you would use this one. Those are the two most common. Okay. And then PV equals nRT just means that we've rearranged the elements of this equation so that they're all on one line. Put everything in the numerator, right? So we had PV divided by NT equals R. But if we take the denominator and put it over here on the other side of the equation along with the R, this is what you get. PV equals nRT. Now this statement is a little misleading, right? If R is not used. If R is not used, then you're back to the situation of before and after. Right? P1 V1 over N1 T1 equals P2 V2 over N2 T2. That before and after, combined gas law. Under those circumstances, the only unit of measure that must be observed is temperature. It has to be absolute units, K. Now there's another system that's derived from Fahrenheit, but it's not used much. Maybe engineers might use it. It's called the Rankine, and it's just based on Fahrenheit. But for our purposes, we're going to stick with K. The rest of them, if you're using before and after, it doesn't matter what these units are. As long as they're the same on both sides, then they cancel. But for very good reason, temperature has to be K. Otherwise, the ratio is wrong. Why? Because the ratio of any other system other than absolute has negative numbers in it. Right? Celsius could have negative numbers in there, and then the calculation will not work. So we need a positive number only measure, and that's K. Okay. You can arrange the equation in multiple different ways. Right? If you're solving for P, it looks like that. If you're solving for V, looks like that. Solving for number of moles, right? And some problems that I've given you or will give you do want to know how many moles. Why would we want to know how many moles of a gas? If you're trying to determine the molar mass of a gas and you're using the gas laws to determine those moles, then you would solve for N. And you would also have to measure the mass of the gas that is represented by that many moles. If you know the mass and the moles, you calculate the molar mass. Okay, so there are a number of ways to you could even solve for a ratio. Right? If you want to know the ratio of moles per volume, like moles per liter, then you could just make that whole term, the quotient, an unknown. But you have to be sure you got the right units. And then, of course, if we solve for R, like I did on the board just now. Okay. So when you're reading a word problem, you need to ask yourself, well, does it have to do with gases first? And then, is it a before and after type of problem, or is it a state problem? Okay. So how would you do that? Well, you look for a multiple. Like say 2 moles of gas is 37 degrees and 50 liters, but we changed the temperature to something else. Now what's the liters? That's a before and after. You have to pick the right law or use the combined gas law. Oops. And then you say, all right, which one of these is changing from one side to the other? Right? In this case, we were saying maybe 2 moles is constant, right? 2 moles cancels out. Temperature changes. All right, keep that one, keep that one. Volume. Volume is changing, say, going from that one to that one. Pressure stays the same, cancels. Now we know that we can use V1 over T1 equals V2 over T2. Right. So the combined gas law is very useful. Right? You just have to decide which ones are constant, those cancel, and leaves you with the ones that vary. That's if your problem is before and after. This problem is not. This problem is a state situation. So we're saying, calculate the pressure of a system where 2 moles of gas, right? Well, actually 2.0. 2.0 moles of gas at 37 C plus 273 equals 0, let's see, 10, 110, 11, 310 K, and occupies a volume of 50 liters. Right? So what do we not have here? Well, we have pressure. That's asked for. Under those circumstances, you know you have to use the ideal gas equation. Right? So P, if this one, then P would be nRT divided by V. Okay? And the units of measure tell you that you need to use 0.08206 liter atmospheres per mole K. Plug in those numbers, and you get P. .018 atmospheres under those conditions. Here's another situation. Calculate the moles of gas contained in 150 liters at minus 15 degrees C and 850 millimeters of mercury. So now, and remember in the very beginning, I mentioned that a complete description of gas is derived from these 4 measurements. So now we have 150 liters. We have minus 15 C. Okay. And we have 850 millimeters of mercury. That's not in atmospheres. How do you get atmospheres? Divide by 760. And that'll give you atmospheres. Atmospheres, liters, K, and this is your unknown. How many moles? That's why I like to put it on the board like this. Extract it from the word problem so it more easily resembles a formula. You know where your unknown is, you know the values, and this is especially important if you're doing before and after problems, because if you put a before value in an after position, then you're going to get the wrong answer. Right? So you need to set it up and slap it on paper or a board or something so that you know where each one is and whether it's actually one of these values, or if you've got a before and after problem, you don't want to put the wrong value in a position in the formula, because mathematical formulas are like computers, garbage in, garbage out. If you put the wrong values in there, it's going to give you the wrong answer, and the formula could care less. Okay, so there we have our conversions, and then we put IGE means ideal gas equation. Put in the values, cancel, and solve. 7.919 moles. Now, yeah, 1, 2. Actually, there should be a period here, so that at least gives us 3 significant figures. So this probably should be rounded off to 7.92 moles to follow significant figures rules. Okay, now what can we do with all this? Well, working with gases, the way we've done so far is more physics than it is chemistry. So we're going to look at how, how we can make the physics of gases work for us in chemistry. So if we have this reaction, 2HGO, right? Mercury 2 oxide is a solid, and we're going to heat it. In fact, I think it was Joseph Priestley who first turned a big, like 12-inch magnifying glass onto a sample of mercury 2 oxide within a vessel and decomposed it by heating it. And he noticed that it produced this mercury liquid, and they knew what mercury looked like, so he knew it was mercury. And he also produced a gas, and he caught that gas in a water trap. They call them pneumatic troughs. And he characterized this gas. What would it do? Well, it supports life. It makes you feel good when you breathe it. And it also makes a flame grow bigger. Right? It supports a flame. It's not flammable, but it supports a flame. Well, he took that information to Paris and offered it to Lavoisier. And Lavoisier wasn't surprised because Lavoisier had already decided that the accepted theories about matter and gases of the day, the phlogiston theory, was just a bunch of bull. And he and many other chemists in Europe at the time were doing experiments, quantitative experiments that were debunking this theory. But he also worked with it. But Lavoisier took it one step further. He actually measured the amount of gas. He took the mercury and combined it with oxygen in a vessel in such a way that he could measure how much volume decrease of the air was required. And he said, okay, that percentage of the air is required to turn mercury into this compound, which he called a calx. Which is basically any metal oxide, we know now. And then he took it and repeated Priestley's experiment and decomposed it and captured the gas. And he found that the amount of gas required to make this stuff was exactly the same amount of gas required that was evolved when he decomposed it. So that was a major step forward in modern chemistry. In fact, Lavoisier is often credited with founding modern chemistry. Okay. So after that little story, we'll get back to the meat of the subject. Okay, so we have two mercury liquid plus oxygen gas. Okay. Now that equation needs to be balanced before we can do anything with it. 2 oxygen, 2 mercury, 2 mercury. We're balanced. Now here's the problem. We want to know the mass of that solid needed to produce 220 cubic centimeters or 0.22 liters of oxygen at 25 degrees and 740 millimeters of mercury. Okay, this is a stoichiometry problem. So what are we given? We're given 0.22 liters of oxygen. Oops, that means liquid. Liters. There we go. And under these conditions, we want it to be 25 degrees and 740 millimeters of mercury. So what's the first rule in stoichiometry? Well, second rule. After you balance the equation, the second rule is you can't go anywhere in this equation unless you have moles. Have to have moles, or you're stuck. So do we have enough information? Well, if we're dealing with a gas, look, we've got volume, we've got temperature, and we got pressure. So what's left? Moles. So we convert these values into moles using our universal gas equation, or the ideal gas equation, excuse me. And then, now that we know the moles, we can use the stoichiometric relationship between oxygen and mercury 2 oxide and find out how many moles of this would be required to produce that, then convert the moles to grams. Okay, that's the problem-solving strategy here. It all focuses on moles. You can't go anywhere unless you know moles. We've got a gas with these conditions, moles. We're good. Right, so we got volume in liters, we've got temperature in K, we've got atmospheres for pressure. Rearrange the equation to solve for moles, plug in the values. We find that we have 8.755 times 10 to the minus 3 moles of oxygen. Right? Then we do the stoichiometric conversion. It's that many moles of oxygen, and the ratio is 2 moles of mercury 2 oxide for every 1 mole of oxygen. There's 1, there's 2. So now we can calculate, well, we're going to do it all at once, but what we would do for logical steps, we'd find out how many moles of mercury 2 oxide, then we convert those moles, here, moles, to mercury 2 oxide. We need to know the molar mass, right? So you just take mercury, let's see, 200.59 for mercury, and then oxygen is add 16 to that. We cancel the moles, and we end up with this many grams of mercury. Okay, that's a stoichiometry problem using gases. Next question, after you know the mass of the mercury 2 oxide, we also want to know something about the mercury that's produced in the process. So what volume of mercury would be produced? Well, look, the ratio is the same from 1 oxygen to 2 mercury 2 oxide, 1 oxygen to 2 mercury. So it's going to be the same number of moles of mercury as mercury 2 oxide. It'll be a different mass, right? Because it's an element, not a compound. So you use that equivalence, convert it to mercury, right? 200.59 grams per mole for mercury, right? So now we have grams, and now we want to convert grams to cubic centimeters, right? So we need to cancel grams. So we invert this one, put grams on the bottom, like that, see? Now we can calculate the cubic centimeters. So at 0.258 cubic centimeters of mercury, which is not a lot, really. Okay, I mentioned earlier determining the moles of a gas and the mass of that same amount. If you can get both of those values, the moles of the gas and how much does it weigh, then you can calculate its molar mass. Now, why would that be valuable? Well, remember when we were doing composition, we had percent composition, and we were determining the empirical formula for a compound. But we couldn't get the molecular formula until we had the molar mass of the compound. There are a number of ways that you can do it depending on what type of compound it is. If the compound is liquid, then, and it's volatile, you only have to heat it up just a little bit to make it vaporize, then we can use this method, the Dumas method, to determine the number of moles and the mass, and we're going to use the gas law to do it. And that way you can determine the molar mass of a gas, or of the liquid itself actually, to fill in and complete the puzzle from empirical to molecular formula. You don't have to know the formula of the gas to do this. You just need to know that it has a low boiling point. Right? Something below the boiling point of water is probably best. All right, this fellow right here, this Frenchman, Jean-Baptiste André Dumas, lived in the middle 19th century. This is not the same Dumas as the one that wrote The Three Musketeers. This is a different Dumas. This wasn't his only area of expertise. Like I said, in the 19th century, everybody was working on organic chemistry. Even non-chemists were trying, they're dabbling in it. But in the process, he discovered and developed methods for determining molar mass. Because a lot of the organic chemicals that they were investigating were volatile at reasonably low temperature, like the boiling point of water, something less than that. So they could use a method to determine the molar mass of the compounds, and then they could do their percent analysis to get the empirical formula, use this method to find the molar mass, and then they could finish by defining the molecular formula for the compounds. This is just a word of warning. There's more than one Dumas method. Right? This Dumas method is the one that we're interested in, working with gases and determining their molar mass. But there's also another Dumas method that is associated with the analysis of organic compounds. And it was developed by the same guy. All right. So in order to derive a useful equation so that we can do the calculation in one step, we take the ideal gas equation and the equation for molar mass, which I abbreviate molecular weight, MW. And in order to know the molecular weight, you need to know the mass divided by the moles. So we get the moles from this equation. We just solve the ideal gas equation for moles. Right? Well, we solved this one for mass divided by molecular weight, and then we equate it to moles. So PV equals, actually we're substituting backwards, excuse me. We're solving this one for moles because that leaves us with molecular weight in the formula. So that makes perfect sense. If we're solving for molecular weight or molar mass, we want that to be in the equation. So this makes more sense. Substituting this mass per molecular weight for N, we get this equation, and then we solve it for molecular weight. So here we need to know the mass of the gas that's been determined, the volatile liquid. We need to know the gas constant. We need to know the temperature at which it occurred. If you're doing it in a boiling water bath, then that's simple enough. You just measure the temperature and convert it to K. Right? The temperature will vary. Boiling water bath will vary, so you need to measure it. Especially if you're at elevated altitude, like here, we're a half a mile high. So the boiling point is going to be a lot lower. And then you need to know the pressure. So you read that off a barometer, and whatever it happens to be, you convert it and make it atmospheres. Right? It has to be in the right units to use the R value. And then volume you convert to liters. What's the volume of the vessel in which the gas is confined? And then you plug all these numbers in there, got the molecular weight. That's one of the experiments that we're going to be doing, I think, in this class, in the lab. Let me be sure. I don't want to tell you wrong, but I think this is the appropriate time for it. Yep, it's the last one, or the next to the last one. Let me look again. Yeah, it's the last one. Okay. So these are the conditions in the Dumas method. And let me see how much time I have. There we go. And this class goes till 3:45. Okay, good. We got just under an hour. So in this experiment, we use in this case, a 250 milliliter flask. Now that 250 milliliters is a nominal value. In other words, the flask will be like that, and you'll have a mark on here somewhere. Right, that says that's 250 milliliters. Well, the whole flask is more than 250 milliliters. We need to know the entire volume of the flask because that's going to be the confined space for the gas. We're going to have it capped off here. So it's going to be more than 250 milliliters, and you have to measure that. Okay. So with this flask, and it has a lid on it, that's aluminum foil. The total weight was 325.2546 grams. Then we put a excess amount of volatile substance in there, liquid. And then we placed it in boiling water. This must be close to sea level for it to be 99.7 degrees C. That should be a degree up there. Convert that to K, just might as well go ahead and do it now. And the barometric pressure we measure at 710 millimeters of mercury. Convert that to atmospheres. And then we cap it off, and we put it in the boiling water bath as far down as possible, and we put a clamp on it, right? Because if you try to submerge a flask that's nothing but gas inside, it's going to try to float, right? So you put a clamp on it, on your ring stand, and you lower it in and clamp it down. So it's almost completely submerged. You want all the gas inside to be the same temperature as the boiling water. And then we vaporize the liquid in that flask, and it shoots out through the little pinhole. Right? There's aluminum foil here, cap. And it's cinched down with a piece of copper wire. So we punch a little pinhole in it, and then the liquid down here vaporizes and fills that whole container. Now, we want to be sure that the entire container is filled with nothing but this vapor. And we don't want any liquid left, right? Because we're interested in the gas. That's why we put excess liquid in there. So we be sure and expel all the air and nothing in there but the gas. sometimes you can see the convection currents, right, as the gas escapes through the pinhole. It's difficult. So we just time it. Say, it's going to take this long, and then we add a few minutes to be sure that it's all gone. And nothing in there but that. Now, why do we use a pinhole? Why don't we just leave the cap open? Because you get eddy currents. As this stuff escapes, it could form vortexes, and air can get back in the flask. So we have a little pinhole there. It can get out, but nothing comes back in. Okay, so now we let the flask cool. So why is that? If you don't let the flask cool before you weigh it, then your liquid is still vapor. And if you put it on your balance hot, the balance will never settle down. It doesn't like heat. Creates convection currents, and the balance will show mass here, and then here, and then here, and then here. Plus, once we pull that cap off, we don't want any gas left in there. We want it in liquid form so that it won't vaporize. Okay, we also want to remove any water, right? We're looking for experimental error. And that could be, if you've got any water clinging to your flask, it's going to artificially elevate the mass and change your molecular weight. It won't be accurate. So we weighed the flask before, now we weigh the flask after with the same attachments as before. Now that's the mass. We got the mass. Now we need the volume. So we fill this thing up with water, right to the level where we think the cap was confining it. And then you have two choices here now. You can either pour that water out into a graduated cylinder and measure it, which is what we do in the lab, in this lab that we're going to conduct. Or you weigh the flask again, and you subtract the mass of the flask from the total mass, which isn't this anymore. It's going to be something like 575 or 580, or it's going to be pretty high. And the difference there is the mass of water. So how do you get the volume from the mass of water? Well, we know the specific gravity of water. It's just a hair less than 1 gram per cubic centimeter. So you convert that mass into volume. That's one way to do it. And it's going to be in cubic centimeters, so you convert that to liters. Cubic centimeter is a milliliter, right? Which is 1,000th of a liter. So you take that value and move the decimal place to the left 3 places. You got liters. Now you got all those factors together, and you can plug them into the formula, right? There's the mass of the liquid. Rearranged for molecular weight. We know R, we know mass, we know temperature, we know pressure, we know volume. Solve for molecular weight. Now, the mistake that's made here, we're assuming for this calculation that the flask is actually 250 milliliters or 0.25 liters, but it's not. It's going to be closer to like 280, 285 maybe. So this is just for illustration purposes. In reality, it's going to be higher than that. But once you do the calculation, we find the gas, in this case, is 152.98 grams per mole. Now you could do separate calculations, right? We could go back to here, and we could do one calculation that finds the moles, and then we have the mass, so we could plug the moles in and find the molecular weight, right? You can do it 2 steps, that's fine. But if you combine both equations, then you only have to do one calculation. You just have to be sure that the equation you're using is valid. Okay, so that's the Dumas method that you're going to be doing the very last experiment of this semester. Okay, so let me see. I can't even read what that is. Oh, ideal gas law under changing conditions. So under what conditions, what dynamic conditions, would the ideal gas law be applied? Okay, so under these circumstances, what do you have? The final volume of a gas is 50 liters at 250 C and 750 millimeters of mercury. We cool it down to 25 and compress it to 900. So under those circumstances, which equation would we use? You know, I think we probably want to use the combined gas law. Right? What's the final volume? Right? You got before and after. So this is before and after would best be used. Let's see, the question is calculate the final volume of some gas. Okay. So we have 750 millimeters of mercury. If we use the before-after version, then we don't have to convert to atmospheres. We just use the values. We just have to be sure that they're in the right place. And there's 50 liters, right? Temperature, liters, and it wants us to find out the final volume. So where's V? Well, V is on the other side of the equal sign, right? That's what we're calculating. Now, what about moles? Did the moles change in this process? No, we got the same amount of moles we had before, so they cancel. Those units cancel, those units cancel, we're left with liters. Right? So under these circumstances, the combined gas law would be the best choice. Now, could we use this equation? Well, let's see. What's the final pressure? 900 millimeters of mercury. Yeah, we could put that in. Volume. We solve for volume. Number of moles. Do we know the number of moles? No, we don't. So that's it. You can't go any further. If you don't know the number of moles, you can't use this equation for this problem. Okay. So what about the decomposition? What are we doing here? The decomposition of ammonia to nitrogen gas and hydrogen gas. Let's see, if we start off with 25 ammonia at 400 millimeters of mercury and 25 degrees C, and we heat it to 500 degrees, the vessel expands to 30 cubic feet. So we want to know the final pressure. So is this a before and after, or is this a state function? Well, let's see. We're given volume here. We're expanding the volume to 30. Right? We're changing the temperature from here to here. And there's the pressure. So we should be able to use the before and after. There's the final pressure. The question becomes, what are the moles before and after? The moles before are 2. The moles after are 1 plus 3 is 4. So that makes a difference in the calculation. The moles have changed, in a chemical reaction. On the previous problem, there was no chemical reaction. That was purely a physical problem. But if you're going to decompose something here from one gas to multiple gases in this case, you have to know moles before and after. So what are the moles before and after? Well, actually, it doesn't matter what the absolute moles are. It only matters what the ratio is, right? Here's the moles final, and here's the moles initial. The moles initial compared to final is 2 to 4. So that's what we substitute. 2 gas here, 4 gas there in the final. And then the rest of it is derived straight from the problem. That's the one booger right there. What to put in the moles. If you cancel the moles out, then you'll get the wrong answer, because this chemical reaction produced a different number of moles in the products than were in the reactants. It is a before and after problem. That's true. Right. So there's our millimeters of mercury. Did it ask? It didn't specify. So that's a good answer. Okay. Now we're going to introduce John Dalton again. Remember Dalton's atomic theory? That wasn't the only thing that he did. He was also interested in those days, of course, with gases. But he also had this other relationship law that he had developed that allowed investigation of gas mixtures. Right? Since the ideal gas, every gas in a mixture behaves as if it's just alike to the other gases, then we can treat them as if they're not even there. Although they are there, and we want to know what's the individual contribution of each gas to the total pressure. So Dalton said the total pressure in a vessel is equal to the partial pressure of each, the sum of the partial pressures of each of the other gases. Out to however many there are, each one contributes to the total. So in the Earth's atmosphere, most of the pressure is contributed by nitrogen, because nitrogen is 79%. And oxygen is 20%. Right, so that's 99. So the rest of it is other gases, mostly argon. It's almost 1%. Then there's some carbon dioxide, and there's some other pollutants that man has added over the centuries. So in addition to this partial pressures that we know of, that also relates numbers of moles. Because we know that from Avogadro's law, that if you increase the number of moles in a container of gas, the pressure goes up proportionally. If you double the number of moles in a container, you double the pressure. So that's what this means. Right? If the total pressure is equal to this, then each one of the number of moles of gas in that same volume leaves us with a relationship that says the total pressure is, we can add up all the individual moles, and those individual moles, their ratios to one another are also the ratios of the pressures to one another. So how do we make that value useful? If you ratio the pressure of, say, this one to this one, That's the same as ratioing the number of moles to the total number of moles. And that has a special variable sign. The ratio of the number of moles to the total is a fraction, right? If you add all those fractions together, you get 1. So this is equal to the mole fraction of gas 1. The number of moles of the gas of N1 ratio to the total moles is a fraction. And it's also equal to the partial pressure of 1 ratioed to the total pressure. So that way, if you can measure the pressure, individual pressures of each gas, then you can say how many moles there are for each gas. Okay, and the total of these mole fractions, and that's, we call them mole fraction for a reason. The total of all the mole fractions in there, if you've accounted for every gas, is equal to 1. Because 1 is the whole. And this is another way of saying that mole fraction is equal to the partial pressure of the gas over the total. If you know the mole fraction of the gas times the total pressure, then you can calculate its individual partial pressure. All right. Let's see. So we're going to take an example. This is the detonation of nitroglycerin. There's nitroglycerin. Right? And the reason nitroglycerin is so useful as an explosive is because, and this is the gas, but normally nitroglycerin is in liquid form or actually absorbed to a support medium, like dynamite, uses diatomaceous earth, a special kind called kieselguhr. And you put nitroglycerin in there, and as long as you're careful with it, it's not shock sensitive. It's only when it's in the liquid form that it's shock sensitive. So if you ever run across a box of old dynamite and you're crazy enough to open the lid and you see those sticks of dynamite in there are sweating, that's not water. That's liquid nitroglycerin that is seeped out of the stick. In that case, put the lid back on very carefully and post a sign and go get professional help, because any slight jarring of that case of dynamite will explode. Okay, so the reason that nitroglycerin is so effective as an explosive is it goes from 4 moles of nitroglycerin to 12, 22, 28, 29 moles of gas, like that. Right? When it decomposes, it makes all of these gases, and it has to have some heat with it too. You know, it's an exothermic reaction. But the explosive force is the creation of 29 moles of gas out of 4, just instantly. And you know from Avogadro's law that pressure will go, by ratio, 29 to 4 is somewhere between 7 and 8 times. Pressure will increase that much. Okay, so if we detonate this in a controlled environment with a safety vessel and a very small amount of nitroglycerin, then under these circumstances, if we put that nitroglycerin in a 100-liter vessel, which is pretty big, and at 25 degrees, 20 millimeters of mercury, it detonates and the vessel expands to 110 liters. and the temperature rises to 400 C. So what's the pressure? Well, under these circumstances, we actually don't need that temperature. Yes, we do. This is before and after. Right. So we have information that gives us before and after conditions. We notice that we're going from initial pressure of 20 millimeters of mercury to some other value that we're solving for. The initial volume is 100 liters. The final volume is 110. Right? So there you go, those two values. The final temperature is 673 K. The initial temperature is 298. Now, how do we do the ratio of moles to moles, final moles to initial moles? We use the stoichiometry, use the balanced equation. 29 moles of gas is the final number of moles, and the beginning number of moles is 4. So under those conditions, we calculate that the increase in pressure from 20 millimeters of mercury, which is it's not quite a vacuum, but it's very low pressure. It goes from 20 millimeters up to 297 millimeters. Okay? So I imagine that the reason we were starting out at 20 millimeters of mercury is with that low pressure, then when we release all this energy in these gases, it won't overpressure the vessel. Okay, so now that we know total pressure here, what's the partial pressure of each one? Remember the mole ratio? So this ratio to the total of 29 would be the mole fraction of CO2, 12/29. All right, so that ratio gives us 123 millimeters of mercury is attributed to carbon dioxide. Same thing for water, 10/29 ratio. It's a little less. Nitrogen, a little less. Oxygen is almost nothing. Okay, so those are the partial pressures, and we understand the mole fraction to be derived from the equation, right? This is the mole fraction, that fancy X, right there, mole fraction for CO2 is based on the stoichiometry of the balanced equation. And we check to see, add them all together, and you get pretty close to the original. Yeah, missed it by 0.02. Okay, so up to this point, we've been talking about laws. Now what we need is a theory to explain why these laws work. And that is the kinetic molecular theory of gases. Molecular theory, that is, the gases are composed of molecules, in some cases atoms. But molecular implies each particle in there acts independently. And then the kinetic molecular theory implies motion. Things are moving. Every molecule in that gas is moving, in fact, at very high velocity. So what's going to happen? Well, there are large numbers of particles, even though gases are considered they're very far apart from one another compared to liquids and solids. Right? The distance between them is huge. But there's still a lot of them. I mean, even at a tenth of an atmosphere, you've still got billions of atoms and molecules in that confined space. So there are large numbers. Why do we need to consider large numbers? We need the averaging effect because we can't measure the distance, the direction, and the energy of each one individually and put it in a supercomputer and calculate anything about them. There's just too many. So we just say, all right, well, let's go with large numbers. And we'll just take the average effect of that many. Make it a statistical problem. We still believe that the particle size, or the molecular size, is small compared to the distance between the particles. Okay, so that's our ideal gas. And that these gas particles are moving very rapidly. Right, so what does that mean? That means they get from one place to the other really quick, unless they smack into something, right? Which they usually do over a distance of picometers. They bang into another molecule. These collisions, as I said, are inevitable. They will happen, and large numbers of them will happen. Now, we also have to insist that these collisions happen not just between gas particles, but with the walls of the container as well. And for the same reason as before, if they don't bang up against the wall, we can't measure the pressure. Now, here's another one that's important. The kinetic energy of the molecules in the gas is proportional to the temperature. So if we increase the temperature, then the molecules are going to have more energy, they're going to move faster, and they're going to bang into each other and the walls with greater force. So when they bang into the walls with greater force, that means we're going to measure higher pressures. And that explains this relationship. Let's see. That explains that relationship, right? As temperature increases, pressure increases. Okay, so that point number 6 explains that. Now, we can't measure the kinetic energy directly of each molecule, so that's where the averaging effect comes in. So at any given temperature, the average kinetic energy increases as the temperature increases. You will have probably a bell-shaped curve, right? If you have energy here and numbers of particles here, you will have like that. And most of them will be in here. But they won't all have the same energy. So we say the average kinetic energy changes with temperature. And of course, we have to assume that when they smack into each other, they don't interact. Right, so these are postulates of the kinetic molecular theory. Now, how does that explain what's going to happen? Well, we're going to use an analogy here. And what I'm leading to is, with this analogy, why this averaging effect as temperature increases, the average molecular, the average kinetic energy of the molecules increases. It's not a simple average, though, right? And this next couple of slides will show you that that averaging has to be done a special way. Right? So let's go back to the bowling balls, each one weighing 5 kilograms, right? So that's a 11-pound ball, a little over 11 pounds. I don't know, what's the average bowling ball, 10 pounds or 12 pounds? Not kids, but adults. So we're talking about a bowling ball here. And we're making it 5 kilograms just for easy calculation. So how do we calculate the kinetic energy of any object? Well, the kinetic energy is equal to 1/2 times the mass of the object times its velocity squared. Okay, so the energy is going to increase proportional to the mass, but proportional to the square of the velocity. So when an object is going twice as fast, it actually has 4 times as much energy. That's why when you increase your speed in your car from 30 miles an hour to 60 miles an hour, the devastation from a crash is not just twice as bad from 60 miles an hour than 30 miles an hour. The devastation from a crash at 60 is 4 times as bad as it is at 30. All right. So these are the values, and let me show you where those values came from. The joule is a derived unit of energy. Right? We use fundamental units from the SI system and derive energy units using this equation. I usually write it this way: kinetic energy equals 1/2 mv squared. So let's look at that equation for units of measure only. So if this unit is kilograms, which is the SI unit for mass, and this one is meters, velocity is meters per second. Meters is the standard length, second is the standard time unit. And then we square them. The units now are going to be kilogram meters squared per second squared. Right? And one of those is equal to 1 joule. Okay? That's where the joule comes from. It's a derived unit. Okay. So if we do that calculation for this 5 kilogram mass, then at 10 meters per second, it has 250 joules of energy. Right, just plug 10 into the velocity, square it, 100 times 5, and then 1/2 of that is 250. Okay. Right, so if we do 1/2 times 5 kilograms times 10 meters per second squared, right? 10 squared is 100, times 5 is 500, times 1/2 is 250. Right? So that's the way we're calculating the energy of this bowling ball. All right, so yeah, that's good. So say we have a collection of bowling balls, 7 of them, and they're incrementally increasing their velocity by 10 meters per second each one. So this one is at 10, this one's 20, 30, 40, 50, 60, 70. And we calculate the energy of each one here. All right, so what would be the average energy? Let's see, what's the average velocity? All right. And a bar over a value like that, in statistical notation, that means average. Okay? So if we calculated the average velocity of each one of these, of the total, just by a simple arithmetic average, 10 plus 20 plus all the way to 70 divided by the total, 7, then we get 40 meters per second. What if we used 40 meters per second and the mass of the ball and find out what its energy would be under those circumstances? Well, we haven't done it yet. I'm jumping ahead of myself. The average kinetic energy based on these values would be an arithmetic average, which would be 5,000 joules. But if we use the 40 meters per second, which is average velocity, simple arithmetic average, and use that value to calculate, well, actually what we're doing is, this is the average energy, kinetic energy here, and this is the mass of the ball. Then we calculate that the velocity of one ball to give you that amount of energy would be 44.72 meters per second, not 40 meters per second. So what's wrong here? The arithmetic average is not the correct one for calculating energies of collections of objects. What we need is some way to calculate this value so that if we use it in a kinetic energy formula, it will give us the true average kinetic energy, right? And the way we do that is called, let's see, is it going to give it to us? Let's call the root mean square. Here it is. RMS means root mean square. So you may have never heard of this expression before, but you use it every day. When you go to your wall socket and plug something into it, to use that electricity, what comes out of there? It doesn't come out of there like this, at a level voltage like that. No, the voltage that comes out of your wall is alternating current. This is direct current. Alternating current looks like it's a sine wave, right? High voltage, low voltage. It crosses the center line. And notice that sometimes the voltage is 0, right here. Sometimes it's high, sometimes it's low. The actual voltage that comes out of there is, see if I can remember. It's about 135 to 38 volts. Let's just say 138 positive, and then negative 138 volts. So, in order to do calculations with this type of voltage, we need to know its equivalent to DC in order to do calculations like Ohm's law and so forth. So notice it's continuously varying, right? It doesn't just go up like that, back down. So we can't do an arithmetic average. We do a root mean square average. And the root mean square average for this is 115 volts AC. Okay? That's why when you stick your finger in a light socket or you accidentally touch a live wire, then it's not a continuous shock. It feels like a hum, because this is occurring at 60 hertz, 60 cycles per second. All right, so we do a similar type of calculation for velocity. And as it turns out, the root mean square velocity is based upon its kinetic energy, but the calculation itself depends upon the gas constant, the temperature, and the molar mass of the molecule. Right? If it has a certain energy, then we have to take into account both its mass and the distribution of velocities. And we're not going to derive the formula. This is just what it is. You take the square root of 3 times the universal gas constant, the ideal gas constant, and this gas constant is going to be one with joules in its makeup, 8.3145, I think, something like that. and temperature is Kelvin, and molecular weight is, I think molecular weight has to be in kilograms. Kilograms per mole. Why? Because that's the standard unit. And if you don't put it in kilograms, you won't get that unit resolved in the calculation. So there it is, joules per mole K here, temperature, molecular weight. And molecular weight, it has to be in kilograms because of, and I'll go back, because of this right here. Because the joules equivalent is kilogram meter squared per second squared. And if you're going to resolve that in terms of velocity, then you got to cancel out the kilograms. And you can't do that with grams per mole that we normally do. So when you use this formula, the molar mass has to be in the form of kilograms per mole. All right. So let's take a real problem and calculate the average velocity of air. The average velocity of air, it'd be kind of hard to do unless you have a way of estimating the effective molar mass of air, right? Because dinitrogen is different than dioxygen, and those are the two major components. So the average molecular weight of air is, we just give it to you, 29.02, right? 2 nitrogens is 28.02, and 2 oxygens is 32, excuse me. But there's only 0.2 of that is oxygen, and 0.79 is that of, so I could show you the calculation, but just know that you need to use an effective molar mass, and we have to convert it to kilograms per mole. Right, there's the conversion. So now the velocity of air is equal to square root of 3 times RT divided by the molecular weight of air. Right, that's simple. So we put the values in, and notice here we've changed the units of the R value to take into account kilogram meter squared per second squared, so that we can cancel units. Right? Moles cancel, kilograms cancel, K cancels, and leaves you with meters per second, meter squared per second squared, but it's underneath a square root sign. Right? So when you take the square root of this calculation, you reduce that square to single units, meters per second. So the velocity of air on average is 500 meters per second. That's pretty fast, right? A molecule of air going, let's see, 5 football lengths. Actually, it's more than 5 football length, field lengths in 1 second. And that's only if it's unimpeded. It's going that fast for just maybe a nanometer, and then it smacks up against something, the wall of a container or another gas molecule. All right, so what is that in miles per hour? 1,155 miles per hour. So that's faster than the speed of sound. Right? Speed of sound is in the neighborhood of 740, 50, something like that. What if we substituted helium there? What would you expect if helium has the same energy as air, but helium is a lighter molecule? How does it obtain that much energy if it's a lighter molecule? It has to go faster. Right? Speed. If it goes faster, then it can have the same energy as air, even though it's a smaller molecule. So if we substitute that in here, we find out that it's 1390 meters per second instead of 500. Right? Almost 3 times as fast to make up for the difference. Okay, one last law. We've talked about the kinetic molecular theory of gas, and there's a law that was developed by Graham called the Law of Effusion. Sometimes it's written the Law of Diffusion. And you understand what diffusion is. If you open a bottle of perfume in a room, pretty soon you're going to smell it on the other side of the room. You don't have to do anything, just let it sit there. The molecules of the perfume will diffuse through air to the other side. They do it at a certain rate, and that rate depends upon the molecular weight of the gas. Right? The lighter the gas, the faster it moves. So the faster it moves, the quicker it gets there. And we can use this relationship to determine the molar mass of an unknown gas. Just like we did with Dumas, well, not just like, we're aiming for the same result. We want the molar mass, but this is a different procedure. But it doesn't matter what the gas is. You can determine the molar mass of an unknown gas by comparing it to the diffusion rate of a known gas. So this is what the equation looks like. We're developing the equation, right? We're ratioing the velocity of one gas to the other, right? It could be a positive value or a negative value. If velocity of A is higher than B, then it's going to be a positive value. And in that case, the A molecule would be lighter than the B molecule because all of this is occurring at the same temperature. So everybody has the same average molecular, the kinetic energy. So what this turns out to be, using that relationship of velocity, right? We just ratio one to the other, and then we reduce the equation by canceling the common values, and it turns out that the ratio of the molecular weight of B divided by the molecular weight of A, square root of that quotient, is the same ratio as the velocity of A to B. Now, how do we measure the velocity? Well, you're looking for a ratio. So one example is if you have a long glass tube and you put some cotton balls soaked in each of these volatile compounds in each side, and you have some way to measure where they meet in the middle, the lighter one's going to get closer to the other side before the other one has a chance to. So the lighter one's going to move over past halfway. And if you can measure the position, the place that they meet, then the ratio of their velocities is the same as the ratio of the distance. Okay, so let me see. Example, here we go. If we compared, and we know what these are already, so this is a demonstration. We're comparing hydrochloric acid, or actually hydrogen chloride, because this is a gas. Compare that one to ammonia, and ammonia is lighter than hydrogen chloride. So it should move faster, correct? If they're at the same temperature, it has to move faster. Well, where they meet in this tube, they form a solid, ammonium chloride. And it's kind of a fog. So it's easy to tell where they meet. Right? So if we ratio the distance that ammonia moves to the distance that hydrogen chloride moves, that's the same as the ratio of the velocity. And we set that equal to Graham's, well, this is Graham's law. Set that equal to this expression. Then we can find out Actually, we're working backwards. We know the molecular weight already, so we're going to find out what's the ratio of the distance. All right, so we do that ratio, and we find out that the ratio is 1.463. Right? So if the long glass tube is 150 centimeters long, then the distance that one moves is 1.463 times as far as the other one. But both of them together equals 150 centimeters. That's where this expression comes from. If we solve for x, then x will be the distance that the lighter one moves, ammonia. Right? So x is, excuse me, it's the distance that hydrogen chloride moves. I'm sorry. Because if we multiply this one times that value, then that means we're compensating for the other value. So this is the value that ammonia is moving. So 60.9 from 150 gives us the distance that ammonia moves, 89.1 centimeters. And this is an animation of that tube. Right? So there you find that ammonia moved faster and it ended up over here. Okay, now here's another one. Suppose we have a 120 centimeter glass tube, and we're going to put ammonia in one side and an unknown gas in the other. Now, what are the prerequisites? For this method to work, the unknown gas has to react with ammonia in such a way that it indicates where they meet. If it doesn't, then you can't use it. You can't use this particular variety of experiment. So that's a given. After 5 minutes, a smoke ring appears. All right, so we did have some reaction at this distance from the NH3 side. Right, so if this is the distance that that one moves, and this is the distance that ammonia moves, which is this ratio, then that's equal to the molecular weight of the unknown, which is on the bottom over here, but it's in the top in this expression. Remember that. And this is the known value. Then we can solve for the unknown. And it turns out the unknown is 127 grams per mole. Right? We don't know what the gas is, but we do know what its molecular weight is. All right, so if we have these examples, right, it has to be a halogen. If it's a halogen, it's going to react with ammonia. That's given. So it's hydrogen iodide. Now that tells me also that we have to elevate the temperature some. Because I believe hydrogen iodide is probably not a gas at room temperature. I could be wrong, but I don't think it is. Okay. Last two slides. I used to live in a town when I was a kid in Tennessee called Oak Ridge, Tennessee. During World War II, Oak Ridge was part of the Manhattan Project for the development of the atomic bomb. And it boasted a higher percentage of college-educated and PhD chemists, engineers, scientists, physicists, a higher percentage of the population of those educated people than anywhere else in the country. So the school system was excellent, public school system, which was good for me because I was just starting kindergarten, first grade, second grade up there. So I got a good boost to begin with. Well, that's has nothing to do with my point. What they were doing in Oak Ridge was they were trying to find a way to concentrate uranium in such a way that we reached a fissionable amount of U-235. Right? Uranium occurs primarily not exclusively, but primarily in two isotopes. (238) and 235. But it's very small amount of 235. Right? It's like a fraction of a percent. But that's the one that you need for a bomb. Okay? So there were several methods being used. They were developing ultra centrifuges, right? Because if you spin this material fast enough, then the heavier ones migrate to the outside and the lighter ones stay toward the inside. And you should use those over and over and over and over again and gradually increase the concentration. That's what Iran is doing now. They're using ultra centrifuges to thumb their noses at the world and make an atom bomb. But you can't use uranium metal. It has to be a gas, right? So we convert it to uranium hexafluoride. Now you've got a gas and you can use the ultracentrifuge. But the technology was still not well developed. A better technology, one that was maturing, was using Graham's law. Notice that this lighter one is going to move faster at the same temperature than this one. So if you put them under pressure against a screen, a very small pore screen, then more of the 235 is going to go through the screen. And you stack them. At each stage, you'll have more U-235 go through than you do 238. And you just stack them, thousands of them. And at the end, you have an enriched uranium-235 using Graham's law. The problem was uranium hexafluoride is extremely corrosive to metals. So they couldn't use a metal. Stainless steel even, it would just eat it up. So fortunately by this time, DuPont was gearing up to manufacture a new polymer. They called it Teflon. I think it was DuPont, or was it Monsanto? One or the other. Anyway, Teflon was available. It was resistant to corrosion, and it could be manufactured with small pore sizes. So they created this huge building. DuPont, I was right. They created this huge building here in Oak Ridge called K25. And most of that building is taken up with stacks and stacks and stacks of these filters. But at the end of the process, they had fissionable uranium-235. This is what we used to do for entertainment when I was a kid. We weren't that wealthy, right? But we did have a car. So around these plants, and there were 3 of them that used different methods. This K25 used the diffusion method. They had a fence around it, but there was a road on the outside. And as long as you stayed on your side of the fence, the guards wouldn't shoot you. So we used to hop in the car and go for a ride, and we'd ride around this plant. And it would take us about 15 minutes. It was that big. Now it's more like, yeah, 15 minutes at those speeds in those days, like 20 to 30 miles an hour. And that was our entertainment. And you notice that the difference here between velocities of these compounds was only 1.0043. It's very small. That's why it took so many steps to purify it. But it was done, and it did accomplish the mission it set out to. Now, Subsequently, ultracentrifuges were perfected, and they were much more efficient at purifying uranium or any other gas for that matter. And you can go to this website and you can see more about it. It's got construction pictures, like when it was being built and all that stuff. It's pretty interesting. 44 acres it took just for that one building. It's a mile long. Okay. So last but not least, when we talk about real gases, ideal gas equation is perfectly all right for us at this stage. But for some engineers and chemists, they need to correct for the non-ideal behavior of real gases. And these factors, the differences between real and ideal gases, were taken into account by a chemist or a physicist, maybe it was a polymath, I don't know, by the name of van der Waals. He proposed an equation that corrected for these values. And in fact, he won a Nobel Prize for it in physics. This equation corrects for the variation between real and ideal gases. So this term right here corrects for the pressure differences. And that has largely to do with the volume of the volume that we have assumed to be point and not real. This corrects for the volume. The pressure corrects for the pressure, and this term corrects the volume, right? So this is P. This term would be P. This term would be V, and nRT. You don't have to correct for the temperature. You do have to correct for volume and pressure, and that's what these terms do. Now, this constant, this A and this B, right? The N is moles, and the V is volume, of course. The A and the B have to be experimentally determined for each gas. Right? That's the kicker. But at least you have something to work with. And my guess is that if an engineer is going to use this formula for something, they've got a big, thick book with tables in it. Right? And you can look up any gas you want under any circumstances and plug those values in. Okay, so that is the end of the slideshow and the end of gases. And I'm a little bit over, but not too bad, 10 minutes. All right, so this is Monday. And are there any questions, comments? I'll post that. Part 1 is already posted in Blackboard, and I'll post Part 2 this evening sometime, however long it takes me to process it. And then Wednesday we'll have a review on these on the review document. So work as many of those problems as you can between now and then, and I'll introduce what I think are the most important problems. Ones I won't repeat. I'll just do the ones that illustrate best what I think a chemist should be able to do with the information that we have at this point. Okay? All right. If I hear no objections, we'll end it for today.